So now that we have seen the Schwarzschild case, we're going to discuss the Kerr case, the non-perturbed case, Kerr case. The solution is much more complex, and there are a few things to discuss. Again, these videos are to be regarded as a kind of introductory lessons in quotation marks to because it's the way that I would liked in the past when I was a student to have these topics discussed before being before being exposed to the mathematical description of the theory. I think, at least for me, it's very important to have a physical intuition of what we're talking about, and this is what I am trying to do for you. I'm talking to my students, because these videos are actually meant for a group of students who are attending an online course during these days. So as before, we're going to keep using two-dimensional diagram, but in this case, we're not going to have a spherical symmetry. This is indeed something very interesting, and which basically goes back to the fundamentals, or to the foundation of the theory of relativity itself. If you go to the introduction, for instance, of a book like Wald, you will have a very interesting discussion about reference frames, etc. And I'm mentioning this here because in this book, in the introduction, if I'm not wrong, when the author is describing what people understood with a reference frame, or why there was this this need to understand whether an experiment performed on Earth would follow the same physics if performed in a moving frame, like for instance a ship at the ocean. This book gives you a kind of sociological or historical context which led were the building stones which later led to the theory of relativity. And in particular, in that book, the author, I hope I'm not saying something wrong, because this is just my memory. He mentioned that back in those days, people were asking, so if you imagine that you have a perfect sphere, like a beach ball, something like that, which is very elastic, and you make it rotate along, for instance, this axis. So if you make the rotation fast enough, and the sphere is elastic enough, there will be a deformation, right? So the system will become more oblate, like this. And the question raised in that book, or the question raised back in those days, was how is it possible? Because we need a reference frame all the time. We make the measurements and the experiments that we're making must be put in the context of a reference frame, for instance, this one. So there must be, this was the argument, if I am not remembering bad, there must be a kind of a universal reference frame, and for some reason, this ball knows about this reference frame, and it understands that it must deform along these lines when spinning around this axis. Now, which one is this universal reference frame? This was a topic which was debated for a long time, and it is very interesting, and many people say, well, just keep things, be pragmatic, and stick to the theory, explain to the students what they have to know, and so that they can solve problems. I don't like that approach, and I think it is very important to understand where these things are coming from. So I would recommend that you go to the, I think it's chapter number 1 in the relativity book of Wald, and read it in detail, because it is very interesting. In any case, so I am bringing this up because contrary to the Schwarzschild case, right? Schwarzschild. Contrary to the Schwarzschild case, we are not going to have a spherical symmetry. So our black hole is going to be rotating along this one axis at a given amount, and it's going to be deformed. But still, we're going to be using the two-dimensional diagram that we were using before. But please remember that we do not have spherical symmetry. We're going to have something which looks like this, right? Well, I'm exaggerating it now, but it's going to be slightly deformed. It's not going to be a sphere. So I'm drawing this here so that you understand what I will explain later. We can describe in a unique way, you know that, of course, any point on the surface of a sphere given two angles and a radius. For instance, this point over here, this one here, can be described by projecting it. I mean, if you want to transform it back to the usual coordinates, like this, so you have the projection, right, like this, so that you have here this angle, which you can call it, for instance, theta, and I insist, ancient Greek, theta, and here another angle, which is in English phi, and in ancient Greek p. There's a reason why this is written like this, PHI, and this is because this was not an F, but an aspirated P, so it's P with this kind of circumflex tone on the I, because ancient Greek had tones like Chinese or Norwegian. Anyway, this is the origin, and you know, this distance, the length of this vector is r. So you can describe any point on the surface of this sphere by two angles, theta, phi, and the length of that vector, r. Okay, that should be clear, and that's the origin. Now, you understand that because we're not going to have a perfect spherical symmetry, depending on the angle theta, you will be on a different geometry along this line. So if your system is going to be difficult to draw it here, but imagine that it was more oblate, like this, I don't know, probably like this, and like this. You can see that by moving along theta, you're going to be closer to a sphere, or you're going to depart from the geometry of it, and then you can move along any given theta in this direction by giving a value for phi. So these two angles are going to be very important, and this is why I'm explaining all of this. Now, just to give you a short summary of what we have seen so far, this is the usual Schwarzschild solution in a vacuum, so with no source terms. And what we're going to do now is the following. Remember that, so this is I0 and I0 here. And I was explaining to you, for instance, that you can slice space-time, the whole of it, by defining a Cauchy surface like this, so that if you specify the initial conditions in this space-time, you know what is going to be the trajectory of that word line all the way up to the singularity. In the singularity, we don't know what happens, and it actually does not make sense to ask that question. But one thing is certain, and this is probably the most important point of this lecture. So try to focus on what I'm going to say now. If you specify the initial conditions of a problem in mathematics, of a Cauchy problem, which means that we're going to be solving partial differential equations. If you define in a proper way the initial conditions to your problem, and if you have a working theory in physics, then you do what we do in physics. We predict the future without having to wait for the thing to happen. If we had to wait observationally to see that Andromeda is going to collapse, is going to merge probably with the Milky Way, we would never be able to see that. But we can predict that in the future, the Andromeda galaxy and the Milky Way are going to crash. And this is what delivers a well-formulated theory in physics, right? So you departure from a given point by specifying initial conditions, and then you can integrate your solution, which, you can dynamically evolve your system, which in this case corresponds to deriving the word line, down to the singularity, because this is the limit of our theory. And again, general relativity is very honest, and it tells us exactly where it breaks down. Now, in the Kerr case, we're going to face something completely different. And this is what I'm going to describe now. So this is the this is like a kind of zoom in of the last drawing. This is our Cauchy surface, which is the one defining the initial conditions of the problem that we want to solve. We have, as usual, here the event horizon, and here as well. And the singularity is not going to be located here, but I'm going to draw a dashed line just to remind you where it was located in the Schwarzschild case. This is I plus, and it's very important that I write it here, because for reasons that will become obvious later on. And what is important is that you remember that topologically speaking, the points that, so for instance, this point here corresponds to a given theta and phi on a sphere. So depending on the theta of the point, so by going up and down along the latitude, the geometry will be different. Besides this point, this remark that I just made, the picture is quite similar, in particular from the exterior. As you can see, nothing has changed much as compared to the spatial case. Now, when you cross the event horizon, things are similar as in the spatial case. So you can evolve dynamically along this world line and cross the event horizon. Geometry changes, and you will start to feel a certain incremental of curvature, but you will not get crashed when you get to the old Schwarzschild singularity. Curvature at that point does not blow up. Before it happens, something else occurs. Instead of hitting the usual spatial singularity, there is another radius comprised between the event horizon and r equals 0. So, if you depart from the exterior, you can cross the event horizon, you can reach and cross the previous non-existent, in this case, Schwarzschild singularity, but at some point you will reach another null surface, which is the one that I have drawn here and here. These two are null surfaces, and in the non-perturbed Kerr solution, these two null surfaces are extremely important because of what I'm going to explain now. I'm going to delete a couple of things here now. These two null surfaces can be reached in a finite time, and we call them the inner horizon. We call also these surfaces the Cauchy horizon or the predictability horizon. So all of these rings, all of these names are equivalent, and you will find them in the literature. Now, remember that in the spatial case, the conformal diagram ended in that singularity. We're now, however, crossing it, and if you work out the mathematics of this Kerr solution, you get those two additional new null surfaces that I just drew before. I drew before. And they are called Cauchy horizon for a reason, because once the world line crosses this horizon, and you can cross it in a finite time, any possible world line is correct. What does this mean? This means that our theory cannot predict the continuation of the world line beyond the Cauchy horizon. And this is why we also call it the predictability horizon. I just forgot to mention that contrary to the event horizon, here, which describes an outgoing null surface. When I say outgoing, I mean that the rays of light are going in that direction. The inner horizon, or the Cauchy horizon, is an incoming null surface because, as you can see, if you remember that the flow of time is in this direction, the rays of light are coming in that direction. And you see, this is a big problem because you define your problem in a very correct way. You define a Cauchy slice of space-time. You have a well-defined set of initial conditions, and your theory cannot predict what is going to happen from that inner horizon upwards, which means that our theory is breaking. Our theory is not delivering what a good theory should deliver. So any of these wall lines that I have drawn here are correct, are consistent in the theory of general relativity. There is no preference for, solution 1, 2, 3, or whatever solution. And again, this is not what a good theory in physics should be giving you. You should be able to know quite accurately what is going to happen. It's like you launch a rocket to the moon, and from a given radius between Earth and the moon, you don't know which trajectory the rocket is going to take. So this is not what you want. What you want is to land on the moon. And it seems like general relativity is not giving us of course I'm making a metaphor, a comparison, an illustration. General relativity is not giving you the trajectory of the rocket. So you don't know if that rocket is going to end up on the moon, or is it going to go to Mars? Is it going to wander through space for the rest of time? And so you can imagine the impact that is caused in the, let's call it the community. This is something bad. The only way to know which one of those solutions is the correct one is to cross the event horizon. And then if you had an observer which could cross it and then come back with data, you could probably extend your theory and find out what is a problem. So the only way, as I was saying, is to cross this horizon and come back and give us data from this region here. But of course, this is going to break our holy cone of light. You cannot do that. You cannot move horizontally because you will be moving at a speed faster than the speed of light. So again, if you start in a universe without any black holes in it, which is almost flat, and you put some initial data in it, which is this Cauchy surface, everywhere, which means that you specify the conditions everywhere in the universe, you would expect a good theory to allow you to predict the future, which is our job in physics. In the spatial case, everything is well determined. Starting from the Cauchy problem, you know that at some point you will hit the Schwarzschild singularity, which is the end of time, and that's it. There is something conceptually wrong about the Kerr case. We have a theory that fails about predicting what is going to happen in the future. In that sense, this inner horizon here, or the Cauchy horizon, and you understand now why this is also called the Cauchy horizon, because it is only within that kind of triangle where our theory is well determined. So in this region here, everything is well determined. We know what is going to happen. So this horizon is the predictability horizon. Now, however, we can evaluate the metric inside of the inner horizon. Even if you cannot dynamically evolve a word line, you can evaluate the metric on that right-hand side of the inner horizon. In this Kerr solution, the singularity is a vertical and not a horizontal line, which goes like this. And that should be vertical. It has some inclination, but it should be vertical. So this is really the singularity here. This is the singularity. This singular surface has very important differences as compared to the Schwarzschild case. First of all, and contrary to the Schwarzschild case, and as you can see, it is a time-like singularity. What does it mean? If it's a time-like singularity, it means that it's a place, it is a location, not a moment in time. So do you remember when I was saying in this Schwarzschild case, I was insisting a lot that the singularity is not what you see in these drawings where you have a circle and a point pop just drawn at the center of that circumference. I was insisting a lot, and I said many times that it is a moment in the future of time, in the future, in which you will be squeezed by geometry, because geometry around you is evolving very rapidly. It is as nonsensical as to asking where is located the Big Bang. The Big Bang is not a point, and this is why I dislike so much these cartoons in which you have a singularity which looks like a point, and it's exploding and it's expanding, and you see the universe being created out of that point. That picture is wrong in so many ways. First of all, it is the region of space and time. So if that point is space and time being born, where on the sheet of paper are you placing that point? If the point is the only place where you can place the point itself, I don't know whether I am making myself clear. Secondly, it is not a point, it's a moment in time. And you can actually define very clearly what this means. So there is actually a way to define correctly, I mean, in a rigorous mathematical way, what is a singularity. And this is something that I actually would like to do, but not today in this lecture. In any case, in our solution now, in the non-perturbed Kerr solution, the singularity is not a moment of time. It's a place, it's a location. And you can actually see it, but you must be very careful when you say these words. This is why people say that these are naked singularities, because in principle you could see them. Now, before I draw it, I would like you to remember that it is not a surface. Sorry, it's not a sphere. Remember that we do not have a spherical symmetry in this problem. the singularity only happens in the equatorial plane, so that it has the shape of a ring with a radius that is proportional to the spin of the black hole. In other words, the metric is singular when r square, which is the radius, plus a square, a is the value of the spin, cosinus to the square of theta equals 0. That defines the singularity, and that is giving you a ring. Oops, something like that, but it should be closed. Now, if this is the ring with some projection angle, there is something important to understand about it. Remember, it is a singularity, so the singularity is not part of a space-time. So how can you possibly determine its geometry? And the answer is by studying the boundaries of a space-time. Now, in the spatial case, the singularity is the end of a space-time. So space-time stands up to the singularity, and the singularity is out of the manifold. In the Kerr case, the singularity is a ring, which means that if you are smart enough, and this is the flow of time, and you are falling into a black hole, which is Kerr, if you are smart enough so as to pick your coordinates well, your phi and theta, you could cross the ring without ever touching the singularity. Let me give some width to the ring so that you can understand better what I am drawing here. So I have added some width to the ring so that you can understand better what I mean. In principle, you can cross the center of the ring without ever touching the singularity, which is interesting if you specify in a small way theta and phi. Now, why do people say that you can see the singularity? That's probably misleading, because you cannot see it. The singularity is out of your manifold. There is no possible way that you can see it. What they actually mean is that you can place observers, or if you want, friends, arbitrarily close to the singularity, which can send you information, for instance, with rays of light, 45 degrees, remember, which will reach you in a finite time. So if you had a collection of friends willing to travel to the interior of a Kerr black hole, pick up the world lines in such a way that they would be placed all around the singularity, and choose the time accurately enough, and they would light up their flashlights at a given moment, you could see a ring of light. And this is what they mean when they say that you can see the singularity, because these observers, these points around the ring, can be arbitrarily close to it. By the way, the solution that I'm talking about is unique. So you can prove the uniqueness of this solution at the interior of a Kerr black hole. Sorry, I am making sometimes breaks in the recording of the video because of the kids, and somebody was calling at the door. Anyway, so I was saying that it is important that you know the following. We have been discussing the solutions to this to the Kerr metric beyond the inner horizon, and it's important to remember that all we have been discussing so far is fiction. It's not wrong, but it's fiction. Why is that? Because you are hitting the Cauchy horizon, and from that point onwards, any possible solution is correct. Any world line, so there is no preference for this or that or the other world line in Einstein's theory of gravity, which can mean that, of course, no theory is the ultimative and perfect theory. Theories are always being improved. So what we have been discussing is interesting per se, but it's fiction because we don't actually know what is going to happen on the other side of the inner horizon. What we have been doing is to forget that we cannot evolve any world line beyond that point, and we have been evaluating the metric to get an idea of what space-time could look like around it if you cross that inner horizon, because you can cross it in a finite time. So again, you can cross this inner horizon like I'm doing now, and you can see the singularity because you can see rays of light coming from your friends describing to you what is around the cliff around that singularity, which does not belong to our manifold. Again, taking into account that what we are discussing now is fiction, it is interesting to notice that because of the nature of the singularity, you do not necessarily have to reach the singularity. With the condition that you are moving with a tangent that has less than 45 degrees, you are fine in your world line. And then you can avoid the singularity. If you notice that you are getting too close, then you can deviate from it. You can move upwards and avoid the singularity. And because you can do that, because you can keep on and on upwards like this means that you can extend your space-time. So this line here gets extended like this. This line here as well should be a square, and it's closing with it here. Of course, now everything is out of place. I'm going to fix it now. Now this is more like it. So you see that so you departure from here, and you cross this singularity, which is not present in the Kerr case. You hit the inner horizon, and then in principle, if you could predict your trajectory, you could keep on moving, avoid the singularity, which is here, and of course also here, because this is symmetric, and keep on moving. So you can cross the extension of the original surface corresponding to the inner horizon. We're crossing towards another universe, which means that we're entering into a white hole. As a matter of fact, we have a chain of universes connected via the black hole, because, well, we have this symmetric part on the left as well. This is the usual, by the way, well-known and maybe treacherous, let's say, picture of these multiverses. You can start in our universe, as we have done, and move towards another one and exchange information with people out there without ever running into a singularity. So we could departure from this universe, our universe here, get into a black hole, cross the inner horizon, not touch the singularity, right, and get into a white hole and keep on moving and doing the same thing forever. So you can go to very different universes without ever having to touch the singularity. So to make a summary of what we have seen so far, and by the way, I have not proven anything, you just have to take my word for it until we go through the equations, if we manage to do that. The singularity in the Kerr solution is an actual place as compared to the spatial solution, which is why they call it a naked. It is not a moment of time. It is a ring and you can cross it. This has, by the way, a number of counter or even, I don't know, non-intuitive consequences. For instance, you can go back in time. You can have a so-called closed time-like curve by navigating at constant phi and theta, which means that you can meet yourself in the past. And that's both, I would say, interesting and problematic. Such closed time-like curves are wall lines in a Lorentzian manifold of a particle, of a material particle in spacetime that is closed, which is returning to its beginning point, because as I said, you can navigate it at constant phi and theta, which is why it is closed. These closed time-like curves were first proposed by Jacob van Stockholm in 1936, 37, and then verified by with a solution of Kurt Gödel in 1949, the famous mathematician Gödel, which led to the Gödel metric. However, other different general relativity solutions containing CTCs, which is what we call them, closed time-like curves, have been found, like the Tipler cylinder and wormholes, which you can cross via the Casimir effect, because quantum field theory allows states with, where energy can be arbitrarily large, arbitrarily negative at a given point. If these CTCs exist, their existence would mean, at least from a theoretical point of view, that you can, tour backwards in time, as we mentioned before. However, it is likely it's possible, I don't know, that in the future a well-posed, a well-formulated theory of quantum gravity rules out these CTCs. Stephen Hawking indeed named this the chronology safety conjecture. But to go back to the most important conclusion of this lecture, in the Kerr case, we don't have a problem when we get to the place where the singularity was located in the Schwarzschild case, which was this one here, right? We have an earlier problem before we reach the place where the singularity is located now. We have a problem when we get to the inner horizon, because even if tidal forces are small enough, depending on the mass of the black hole that you have, and even if you can cross it, you cannot predict the evolution of the orbit anymore. A Cauchy problem looks for the solution of a PDE, a partial differential equation, that satisfies some conditions met on a hypersurface on the domain, which is these slides here, remember. Now, the Cauchy horizon is a light-like boundary of the domain of validity. One side of this horizon contains a closed space-like geodesics, and the other side contains closed time-like geodesics. So that I cannot stress this enough. Beyond the Cauchy horizon, although we can evaluate the Kerr metric, we do not know if that singularity is going to be there, since it lies outside of the limits within which we can solve any kind of evolution. In some sense, by doing the exercise of analyzing the Kerr metric at its singularity and its shape, what we are de facto doing is to put in advance a solution which a priori we cannot produce, because there is no Cauchy solution. We do not know whether this solution is at all possible. We do not know if these things form dynamically from regular initial conditions from a well-posed Cauchy problem. We're evaluating the value that the metric gives to us in a place which is out of reach of prediction. So, the time-like singularity is present in the exact Kerr solution. It is not present, by the way, in a generically perturbed Kerr spacetime, and it cannot form from generic regular initial data. Now, when Penrose presented his work, he stated that no observer could see a naked singularity. In more modern terms, if you want, in the modern literature, this is reformulated, saying that it does not make sense to ask what will see an infalling observer crossing the inner horizon, because we cannot predict in advance what is going to be the evolution of this observer beyond the Cauchy horizon, unless you are the observer himself or herself. But then you have the problem that you cannot send that information outside of the inner horizon, because you cannot travel faster than light. So locally, we do not have a problem crossing the Cauchy horizon. It is a global problem. Now, you can imagine the discomfort that this results caused in the community, because a theory such as general relativity, special relativity in general, which has proven to be so robust and so reliable, all of a sudden was delivering garbage. So from a certain point, from a certain surface onwards, you cannot predict what this is going to happen. Now, Penrose himself delivered a conjecture which fixes this problem, and is the following. And in order to understand that conjecture, we're going to look now at this part of the diagram. Okay? I'm going to draw a zoom in of that part, and I'm going to explain what he came up with just by looking at this conformal diagram, which is the advantage of these conformal diagrams. They're extremely powerful, and you can come up to solutions without having to solve Einstein's equations. Okay, so this is a zoom in. Important is to see here I plus. So this is a time-like infinity point. On this side we have a null surface, null infinity surface, I plus. Over here we have the event horizon to the black hole. I have drawn in dashed lines the location of the singularity for the Schwarzschild case, and over here we have the Kerr singularity, which is it is a place and it corresponds to r equals 0. And then I have also drawn here the inner horizon. Now let's assume that someone is moving along a world line, is getting into the black hole from the exterior. This is the exterior, and is crossing the event horizon like this. And at some point that person crosses the inner horizon and keeps on moving. Okay, so the conjecture goes like this. From this crossing point here, which is the crossing of the world line with the event horizon, the observer moving along this world line is going to see all light. Imagine that we have a series of stars located over here, and this observer is going to get all of the light, slopes of 45 degrees, remember that, coming from all stars, all light in the universe along his or her trajectory on the way to the inner horizon. Now, look at this point here. Again, this is a time-like future infinity, because that amount of light corresponds to all the light which will be emitted in the universe where this person came from, and the infalling time, so the proper time of the observer is finite until that person crosses the inner horizon. In the very last epsilon of time before crossing here, in this epsilon, in this final epsilon of time before crossing the inner horizon, the observer would become an infinitely large amount of light, an infinitely amount of energy density before crossing the inner horizon. Because over here, to reach that point, to reach that surface, you need an infinite time. So you have an infinitely large amount of energy density. This would produce an infinitely large curvature. Therefore, that inner horizon, as Penrose put forward, should collapse. And he speculated that it should become a spatial singularity. A spatial singularity. So it should become a Schwarzschild singularity. That inner horizon should collapse and form a Schwarzschild singularity. And we like Schwarzschild singularities because everything is well posed. If you start from a Cauchy initial, if you start from generic Cauchy data, you will be able to find out the evolution of the world line. So this conjecture was a way to save the predictability of general relativity, because you get rid of the inner horizon. This is the way Penrose proposed the so-called strong cosmic censorship conjecture, which restores predictability to Einstein's equations and makes everybody happy. I was mentioning here somebody falling through the event horizon, etc. But you do not need a massive observer. Any passing gravitational wave should do the job. And because the actual universe, as we know for the last few years, is crowded with these waves, a Cauchy horizon should never occur in the first place. So, is this the end of the story? No. Because there has been an impressive, brilliant, and wonderful progress in this problem. Recently, Dafermos and Luk, I'm going to write the names here, Michalis Dafermos with Luk, proved that the situation at the inner horizon is different. Their work proves wrong Penrose's original statement of the strong cosmic censorship conjecture. And this is the paper, The Interior of Dynamical Vacuum Black Holes 1, the C-naught stability of the Kerr Cauchy horizon. I hope that one day I will be able to read this 217 pages paper and understand every bit of it. But I can make a summary of it. In the paper, which I claim to have understood at least the implications of it, but I cannot claim that I have understood the paper because I am not at that level yet, if I will ever be at that level. What they say is that you will form a singularity, as Penrose predicted, but it's going to be a different one. In some sense, you can think of it as a kind of milder version of the Penrose of the singularity that Penrose put forward in his conjecture. It is a weak singularity, where he instead had expected what they call a strong space-like singularity. They call it a strong because it is the end of time, and it does not make sense to ask what happens beyond that point. So Dafermos and Luk prove in this paper that you can actually extend space-time beyond the inner horizon. And even more importantly, they prove mathematically that starting from a well-defined initial condition, it can be extended in a number in any number, of solutions which do not contradict the solutions of general relativity. What does it mean? It means that indeed you can extend space-time beyond the inner horizon, and it can be extended in any number of different ways, without any good reason to prefer this or the other one. The nice thing about their work is that although there exist so and so many different extensions, and none of them is to be preferred over the others, Einstein's equations are not giving us a wrong answer. Einstein's equations, in this sense, are still honest. Because so the way Einstein's equations work is that they take derivatives of an initial configuration of a space-time, and then they allow us to dynamically evolve a world line. However, this applies to a manifold which is sufficiently smooth. The results of Dafermos and Luk, as I have understood them, and if I am saying something wrong, I would appreciate a lot if you corrected me, seem to indicate that while space-time exists beyond the inner horizon, that space-time is not smooth enough for you to work with Einstein's equations on it. So, as I was saying before, in some sense, the honor or the honesty of Einstein's theory has been saved. Even though you can extend space-time beyond the inner horizon, Einstein's equations can't be applied because they cannot, by definition, deliver you solutions. And the consequence or the conclusion of all of this is that you need a new theory, which is what makes this field or this problem so interesting and exciting.